Okay, so in this video, we're going to look at some calculus, right? And so what we talk about is that work is a dot product, right? So the dot product itself is one way of multiplying two vectors. Now, what happens is when you multiply vectors using the dot product, you get a scalar as an answer and not a vector, okay? The vector multiplication is what we call a cross product, and we'll talk about those when we do electricity and magnetism, okay? Sometimes the dot product is often referred to as the scalar product, all right? And it's just simply because a scalar is returned in as its answer. So now, if a force is directed at an oblique angle, okay, and an oblique just means not parallel or perpendicular, right, to the displacement, which is for the most part what will happen in the real world with this concept of work. You must use a dot product to calculate that work performed by the work. Now, we're going to make some of these assumptions that the force is going to be constant. So the constant nature of the gravitational force and the friction force will allow us to easily calculate the amounts of work performed by these forces, right? So there are two ways that we're going to use to calculate the dot product. Now, what happens is whichever method you use, you'll get the same answer. So the first thing is to look at the notation of the dot product. So we'll have vector A dot vector B, right? And remember that little arrow is our vector symbol. This kind of heavy dot is our dot product. And you make it a little bit bigger because if you don't, maybe you confuse it with the multiplication symbol, okay? Now, the first method of the dot product is multiplying the components of the vectors, right? And you may be given these or you may have to find them, but that is the first method. So A dot B can be simply found by using AX BX plus AY BY, right? And so whatever the X components are of A and B, you multiply them. Whatever the Y components of A and B are, you multiply them, and then you add those two results. Now what happens is, this is mostly used when the angle between the two vectors is unknown. It should be is unknown, not in unknown. But you know the components of each vector, right? So if it's given to you in, so I mean, just for example, 4i hat minus 2j hat, right? B would be, negative 3i hat plus 5j hat, right? So you know the components, and you can simply multiply and add, all right? Now, the next one is to simply use a formula, okay? And the formula for dot product, which you'll see looks very familiar to a formula we were just working with, is just simply AB cosine theta, all right? And then these A and B's, these are the magnitudes of the vectors. And this method is used when you know the angle between the vectors. So again, if I just have something like this, magnitude A, magnitude B, and I say that the angle is theta, right? And so I can multiply the two magnitudes times the cosine of the angle. So this method, again, is used when you know the angle is between them. It's the most common method used in physics because A and B to us are specifically like force and displacement, right? Or it could be really anything, right? Mass and weight, or mass and G, right? Because we can do things like that. Just some general information about this dot product, okay? One thing is that if A and B make an acute angle, where theta is essentially less than 90 degrees, right? The dot product is going to be positive. If it makes an obtuse angle, where theta is greater than 90 degrees, it's going to be negative. Remember, we talked about positive work, negative work. When did that happen? When we're between, less than 90, greater than 90. And if they're perpendicular to each other, our dot product is going to be 0. Okay. The perpendicular, it's something called orthogonal. Now, mathematically, when you're in math class, some of the questions you may run into is, are these two vectors orthogonal, which means are they perpendicular to each other? Okay, and all you have to do is find out if the dot product is 0. Okay, and if you can do that, you typically use the ax bx plus ay by method. All right, so here's just a couple of examples using the two techniques. So this says compute the dot product of A, which is 3i plus 3j, and B, which is 4i minus j. All right, and so because we know the components, right, let me use capital letters because that's what's given to us. So since we know the components, we can just simply use our ax bx plus ay by. So we have vector A dot vector B, okay, and so we're going to do ax bx plus ay by, and so we're going to do 3 times 4, right, plus 3 times -1. Don't forget this, even though there's no coefficient outside of j, that there's always an understood 1, and that becomes negative. So you end up with 12 minus 3 is 9. So A dot B for these two vectors ends up being 9. Okay. Okay, so here's another example, but this time we're going to use the angle in between them. So this is very common. This is basically what we'd be doing when we're determining work done. And so we're going to find the dot product of the two vectors in this diagram. So they tell us magnitude is 4.243 for one of them and 4.123 for the other one, and the angle is 50.94 between them. And so we're going to do, right, A dot B, right, so it's going to be AB cosine theta. And so it's going to be 4.243 times 4.123 cosine 50.94. Okay, and so what do we get in return? We'll get this dot product will be 11. So A dot B, okay, would be a value of 11 or an answer of 11, right? So now how does this apply in physics, right? So we've been talking about work. Work is a dot product, okay? So what happens is in physics, most forces will act at an angle to the displacement. So this makes it necessary to use the dot product, all right? And so just here's an example. I'm talking about a skier, 70-kilogram skier is gliding down at 2 meters per second when he starts down a very slippery 50-meter long slope. What is his speed at the bottom, right? And so we're going to use the dot product, right? So we know that work is the dot product of F dot, or the work is the F dot dx, okay, or delta x. So what does that really mean, okay? And I forgot the angle, sorry. It's a 10-degree angle, right, or 10-degree slope. So we're going to do F delta x cosine theta, all right? And so if we just simply look at, here's our skier, right? And so this is a 10-degree angle, right? And so here's the force. It's the weight that's pulling him down, okay? So if we want to use our concept of work and not have to turn this into a Newton's law problem, we're going to say that this angle at the top is 80 degrees, right? So that's going to allow us to use the cosine in this orientation. So we're just going to do 70 times 10, right? Because that's going to be our force, the weight, times 50, which is how long the slope is, cosine 80 degrees, right? And so that's going to be an answer of 6,100 joules, right? But remember, that's not our answer because we're looking for the speed at the bottom, okay? And so, all right, so now we're going to use our work-energy relationship, okay? And so we're going to simply say 1/2 m, right, v squared minus v initial squared equals the work done. And we're going to solve this for v. And so v ends up being the square root of initial velocity squared plus 2w over m. And now we can plug in our numbers. Square root of 2 squared plus 2 times 6,100 joules divided by 70. And find after his trip, he's going to be traveling 13.4 meters per second right after he goes down this slope. Okay, again, we could use Newton's laws to figure this out, but here's just a great example where we can look at dot products. Okay, now up until this point, we're assuming all these forces are constant. After the next video, we're going to start talking about what happens when the work is variable.